Right. Uh, yeah, resolving forces. I mean, if uh, you think about just back to basics for a moment, we you learn that if I pull apply one force towards the right of say 5 newtons of this on this object, and another force to the left of um, say 3 newtons, we know the resultant force on this object is 2 newtons to the right. And then what you might have learnt about from then, what you probably would have learnt about, is where they involved another 2 forces, and perpendicular to that plane. So uh, you'd have the horizontal forces and then the vertical forces, and you might find certainly at the beginning that one plane of forces, or one dimension of forces, cancel out like that. So in this case, that's not hard. But what we're looking at now is what to do if they don't cancel out, for example, like that. So you may already know that the first thing that you do is you look at one dimension in turn, and so we can see that if we look at the horizontal dimension, then we resolve them first separately to the vertical like that, and the vertical one gets resolved separately as well, like that. And when we think about it in that way, we can sort of make a guess, get a rough idea that the object is clearly going to be. If we take it again, we can see that clearly the force, the resultant force. Let's just get rid of some of these. It's clearly going to be somewhere like that. And we can imagine that we don't know what the force is going to be at the moment, but we can see it's going to be in that direction. If something was pulled upwards and to the right, we could sort of visualize that it's clearly going to move in that direction, so we could say the resultant force is somehow in that direction. So I think what I'll do is I will explain how to do it, but I would also like to explain why that method works to some degree. So we use this squared paper. Basically what we do is you take the 2 forces. What was it? So we had 1 Newton, let's say 1 square is 1 Newton. Like that. And so a couple of ways we can do this, but let's look at it this way first. So that's 2 newtons to the right. What you do is you say the resultant force is, well, what sometimes I see people doing is they draw a line parallel to that. And this is the parallelogram method, really. Because if you think about it, all rectangles are parallelograms anyway, so whether these forces are at an angle or not, it wouldn't matter. And so then you do that, and you can see that the result, and then parallelogram rule is you draw it from one end to the other. So I'll colour that in green, do an arrow there. So that green arrow represents the resultant force, and it's a vector. So we have a direction using that diagram. We have a direction, and we have a size. We would just need to take our ruler and measure the length of that side of that arrow. If it was that these squares, each one was 1 centimeter, we just use the scale drawing to work out what the equivalent force, the magnitude of that force would be, and we can use a protractor to measure the angle as well if we like. Now you can also use Pythagoras, can't you? Because this is a right angle triangle, so we could use Pythagoras. However, I have a feeling that in the GCSE specification that's not in there. So despite the fact you have that tool at your disposal, I don't think you get assessed on it. So what I'd suggest you do is use that as a kind of a way to check your working out, check everything if you like. So you could just do the measurements, and then if you're unsure, use Pythagoras to see if it all works out as you would think. I want to show you one other way of thinking about it, though, and this works. This is a much more universal way of doing it. So, of course, what we've just done now is adding forces, but really, more specifically, we've added vectors. So basically, we know we know how to add vectors in for maths. You have a vector like this, and when we want to add this vector here, it doesn't really matter. Vectors don't really have a position; they just have a direction and a size. So when we add them in maths, we stick them end to end, and so therefore, this arrow here is just the sum of these two added end to end. And in fact, we can do the same thing with the original drawing as well. So if we had as long as we follow the same rules, that we always go end to end. So there's the 5 newtons. Take this and we flip it around, make the 3 newtons. Well, to be honest with you, I think that you might be able to see it already. Let's just do it freehand. So it doesn't matter what order I add these forces up, they will still give me the same answer. So if I start off here, I'm going to go 3 newtons. I'm going to start off here, I'm going to go 3 newtons to the left. And then I'm going to go 5 newtons to the right. Then I'm going to go 3 newtons up. And I go to 2 newtons down. So I finished here, F. And I started here, S. And once again, I get the same answer each time. So my favourite way of doing things is just to imagine picking up the arrows and sticking them end to end. The parallelogram rule is using this. We have the triangle rule, which is this one. But I think about it as just end to end, because the end to end, picking up vectors and sticking them end, the beginning of one is put on the end of the other, is how you do it in maths anyway. And it's also how you would do it if it was displacement, for example. So displacement is also a vector. If I imagine a similar situation, that would be somebody has travelled, started here, so let's write S for start, and they travelled 3 meters north, they travelled 5 meters east, 2 newtons south, and 3 newtons. Must have made a calculation. Oh yeah, because I've gone. Okay, let's try that again. So 3 up, I went 4 right instead of 5. So there's 5 right this time, and then 2 down, and then 3 to the left. So this is my end. And once again, I have the same answer. So this is really how resolving forces work. So I will just pause the video there. Maybe we can find some examples. Okay, so we've related to this kind of idea of resolving forces. We have a situation like this, and you see these are quite difficult questions. They come up quite a bit. And I guess part of what we're doing here is so what I've done there is added forces, and then there's something called resolving forces. And what resolving forces does is it's like the opposite of adding forces. It's taking one force and splitting it up into what we call components. So let's just go back to let's look at this example here. That I started off, where we had an upward force of 1 Newton and a force to the right of 2 Newtons, and then the resultant force is this green arrow. Well, if we started the other way around and we had just a single force, so just one person pulling on a rope maybe at that angle to the horizontal and so on, then we can actually do the opposite way around, and we can divide this single force into 2 as I say, two components. So we would say this is the horizontal component, and this is the vertical component of that force. In other words, if we imagine two horizontal forces of vertical and horizontal force, they would be added together to result in the force that we're actually looking at. So that's what resolving forces is, resolving it into the horizontal and vertical components. Now, if we knew, for example, that so basically, let's just say theta, that's the angle to the horizontal, and that's the force. So we could call this bit here F x maybe. There's different ways you can represent this, and we would use trigonometry because the size of this one up here would be the same as there. Like I moved it over here, and this one therefore the length of this vertical arrow, which we can call Fy, would be that one there. So in terms of trigonometry, this would be F cos theta, and this would be F sine theta. Let's just explain how they get that. Well, that would be the opposite. We know that the sine theta is equal to opposite over hypotenuse. The hypotenuse is the original force, the real force, and so to get the opposite, which is the vertical component, you multiply h by sine theta, and likewise cos theta is equal to adjacent over hypotenuse, and it's the adjacent is the horizontal force, and therefore that would be h cos theta, or f cos theta in this case, because the h is what f is. Okay, does that make sense?
Yeah.
So this is how you would get horizontal and vertical components of a force, and this is what we mean by resolving forces, resolving into components, horizontal and vertical components. Now, actually, you don't need to resolve into just the horizontal and vertical components. You can resolve into any perpendicular components. So, in the case of the block here on the slope, we could rather than resolving. So there's a slow, more complicated, cumbersome way of doing this, where you have to. Whoops, that's the wrong tool. You could take this vertical force and this force friction, resolve that into its vertical, horizontal components, and you can then resolve this one into its horizontal and vertical components. But it actually makes more sense to resolve the weight into components which are parallel to the slope and perpendicular to the slope. And that is generally what is done. So the way to it's easy to kind of visualize this by did I? Oh yeah, good. I thought I might have locked it, but I haven't. So if we rotate this, it's easy to kind of see what's going on. So, and then we can then more easily see that as horizontal and that as vertical. It just helps you to get your head around it a little bit better, a little bit more easily. So the reason why this is more efficient is because now I only have to resolve one force into its horizontal and vertical components rather than two. So now the trick is to work out what angle is what and what sort of triangle do I need to draw. Remember that this is going to be the hypotenuse. So it's going to be that. So we make sure some people they draw it down to here, and then they draw. This is the mistake that a lot of people make, and this generally gets resolved if you rotate it. So they do that because it just feels right to do that for some people when they see it like that. But the trouble with that is that vertical line ends up being larger than the original force. So that can't possibly be the case. So it's actually like this.
Yeah.
So we have let's color code these, and we'll color code that one as well. If we're saying, for example, in this situation, that the box is in equilibrium, and maybe we have been given some values and we've got to work out some other values, then this component of the weight must be equal to the reaction force there. And that component of the weight would have to be equal to the friction, right? Which obviously isn't on my diagram because things are not to scale. But if I were to draw those to scale, then that should be what I would get. Now, another way we can think about this is if we take this. Let's try that again. Take this over here. And we flip it around, rather than think about these as components of the force. If I take this, like I said, the vertical component of the component which is perpendicular to the slope, the components of the weight that is perpendicular to the slope should be equal to the reaction force, but obviously in the opposite direction. So if I flip the arrow around, we can then label this blue line as the reaction force. That's way too big though. And label this orange line as as friction, but I would have to flip it around. And then we could label this one as the weight, like that. Now I think I might now expand that all. So it doesn't really matter how we now look at this. We could rotate it back to its original position where weight is acting down. And the thing that I want you to notice about this, this is what we call in physics a triangle of forces. It's not, the other one was also a triangle, but the difference is that these are no longer thought of as components of the weight. They are the reaction force and the friction and the weight. They're the three forces that are in the diagram. And the reason why I've arranged them in this way is because I've done what I did earlier on, where I added them end to end. And what this is showing me is a closed loop. So because we know that vectors, when you add them end to end, you get the resultant. Let's say we started here. The start and the finish are in the same place. So what does this tell me? It tells me that the resultant of these three forces is zero. And if the question said that the system is in equilibrium, then I already know the resultant is zero, and so I could make sure that my triangle is drawn like that. If for example the resultant was not like that, so it'd be something like that maybe, then this would mean the resultant force would be from there to there. But because we know the thing is in equilibrium, we know the resultant force is zero. Okay, so depending on what kind of thing you want to draw there, depending on what kind of question you've got there, then that will affect what how you tackle this question. The other thing I want to say then is that this angle is actually the same as this angle here. So that is another thing that people really struggle with. Like, how do I use this angle to label that thing there? Now, we could try to explain why that is the case as well. So I think that might be worthwhile. So if I rotate this back up again, that's how it really should be viewed. So why is that angle 30 degrees? Well, let's just erase that for a moment, and we'll try to visualize why that angle is 30 degrees. So let's just draw some lines, and they're going to make sure they're sort of dotted lines. They're nothing to do with the forces or anything like that. We're just drawing some dotted lines to make sense of stuff. Let's do black. So we know that all this is going to add up to 90 degrees. And what else do we know? We know that we can see by angles on parallel lines, that this is going to be 30 degrees.
Mm-hmm.
And maybe it's better to look at this bit here. We know that this is, how did we, I'm trying to remember how I did this now. Hang on, let me just pause the video. Okay, so let's actually, rather than using numbers, let's use algebra, because I want to show you that it's always that. It's not going to be some sort of coincidence. So let's just say, we'll call this alpha. Oh, no, let's call it theta. Called it theta earlier on. And I'm trying to prove that this is theta here. Well, if we look at this orange arrow to the force and then the component of the weight, these two angles add up to 90 degrees. So if I label this angle as alpha, then I can see that theta plus alpha is equal to 90 degrees. Okay, basically by definition there. And let's call this angle here beta, and I'm trying to prove that beta is equal to theta. So we can also see from this dotted line and the weight that alpha plus beta is equal to 90 degrees. Well, now you should be able to see if alpha plus, we can switch this around to make it even more visible. If beta plus alpha is equal to 90 degrees and theta plus alpha is equal to 90 degrees, clearly beta has got to be the same as theta. It has to be the same thing, doesn't it? We could prove it more algebraically by simply saying that the left side of both equations are going to be equal to each other. And so like that, and then we can see we can cancel out the alphas, and now we've got beta is equal to theta. So anyway, so this means that, let's just cross out all of this. We'll have it on the video anyway. And we can now label that as theta. Okay?
Yeah.